For lab number 5, you were asked to determine the amount of copper present in a sample. Most likely utilize standard addition and AA spectroscopy in order to do so. Now, I hope you've realized by the time you've finished today's lab that determining the amount of copper present in a sample is just not one number. You can't just say, hey, it's 15,000 parts per million, I nailed it. You have to be able to express that number with uncertainty in order to correctly identify what the quantity of copper is in your sample. So I wanted to show you a little bit of the workup for this because I think you will now be able to do it from here on out in all future labs. So we're going to use this lab as kind of an example of what I'm expecting in future labs. Your graph should have looked something like this, where you added standard amounts of copper using constant volume and volumetric flasks in order to analyze your sample. So your sample here with no standards added, it was shown in triplicate right here on this axis. So with this, you were then able to figure out how much copper was in your original sample by figuring out where your axes, where your trend line met the x-axis, and then back calculating how much was in the original based on how you diluted the original sample down into your volumetric flask. So what that is shown over here, where I have my slope and my intercept for these lines. Then I calculated my x-intercept and I took into account my dilution. Now your dilution is probably different than mine. I did this back in December. Alright, so then I calculated a percent difference for my 15,000, found a 15% difference, not too shabby. But then I need to figure out of that 17,000, how in the world did I get this plus or minus 400? That's a large portion of what we're going to be answering today. You'll also see other things which I'll talk to you about slowly. But to begin with, I first wanted to show you a control I ran to show you that I'm not just making this up and that this does actually work. So here's an example where I did the same thing, standard addition, but I did it on a blank. So just a sample of water that's assumed to have no copper in it. And when I did standard addition, you notice that the Y here around your 0 is so much smaller. So much smaller, in fact, that whenever I did this with two different types of samples, one I believe was water and one had your zinc and your manganese in it, I got 75.8 and 82.9. And so both were intrinsically around 0, much lower than the one that we did where we know there was a definite amount of copper. And you know what? Our water could have had some copper in it because glass is really good at absorbing copper and other heavy metals, and so when we put the water in it, we might actually have had a small amount. Probably not that much, but there probably was some residual copper in it. Alright, so where did I go from here? First off, let me show you the equation in the book that helps you figure out uncertainties. So this is equation 510. This was taken from the 9th edition, actually from the 8th edition of your textbook. And so with this, I wanted to just kind of pull your attention to it. This is all in the chapter you've already read before, but this equation tells you how to propagate the uncertainty. We did this once before, I believe, in our Excel analysis, but I wanted to call your attention to it. Basically, all we're going to be doing is we're going to be using this equation and Excel to get us there. So to begin with, SY is the standard deviation of Y. Now, you could calculate this by hand, or Data Analysis has the Data Analysis Tool Pack, which is wonderful to give you this here. How we got there was you go to Data, Data Analysis, Regression, add your Y range, your X range, tell it your output range, and then it'll calculate it for you. The only part of this that you actually need is this highlighted here in yellow. What these values mean is that your y equals mx plus b line that is shown here on the trend line. This trend line has error about it, and that error here is represented by the standard error. So my slope is my x variable, and it's shown here, and that's plus or minus the standard error. And then my intercept here is similar, intercept plus or minus some amount. So how you truthfully write it is what is shown right here in yellow. So that's my true trend line, taking into account the uncertainties. Now, in addition to that, I now know what my SY is, which is my standard error about the y. So if I come over here to this equation, you'll note the first thing that I did was I took D49, so D49, come all the way down here, and this is my standard error about my intercept, okay? my B, my standard error. Okay, so that's the first step. Then it says divided by the absolute value of my slope. So here's my slope, times the square root of 1 over my count, so I counted, there's 8 data points, plus M13, so that is my average Y. So I took the average of all of these data points. I also needed an average X, so this is the average of all those data points. Then the last piece of this puzzle is I need to be doing the sum of my average X, or my X individual data points, minus the average X squared. So it really doesn't matter which one comes first. So in this case, I took each individual data points, looked at the difference between that and the mean, and then I squared it. And then I took the sum of all of each of those individual data points. Put all that in there, put this whole in the equation, and that tells me that on my line, whenever I solved for my x-intercept, which was 13.95, that was 13.95 plus or minus 0.29. Whenever I then propagate it and undilute it, if you will, that 0.029 turns into 363 ppm, which makes my final answer be 17,000 plus or minus 400 ppm. So a whole lot of work goes into just getting that final propagation of the error. Okay, I had a lot of you guys ask me, how are you going to calculate limit of detection and limit of quantitation for standard addition? Because if you just stick your average in here for your blank, you're going to get huge amounts of error, because these standard deviations and all of this will make it so you need large amounts of copper before you can ever detect it. Instead, what we're going to do is we're going to say LODX and LODY is equal to 3S over M. Because you don't want your standard deviation to be huge, because if it's just 0 plus or minus something, that means your copper and all that stuff, you're going to increase that error rather significantly. Okay, so for instance, let me show you what I mean. So typically you just did average plus 3 times standard deviation equals my average times 10 times plus 10 times my standard deviation. And then at this point, you normally just throw it into the trend line. So that would be equals my LODY minus my intercept divided by my slope. And see how I'm getting these crazy random numbers? Okay, so here it's LOQY. Oops, I forgot to put little dollar signs on those. Drag it over. So see how you're getting things that don't necessarily make sense? What does it mean that my LOQX involves one standard addition? Does that mean I can only add one standard ever, or that I have to add at least one? Well, yes, that's true. You should add at least 1 ppm in order to quantitate, but this doesn't really make any sense. So these are better definitions for LOD and LOQX than these prior ones that we did with last week's lab. So this gives us a total of about 4.7 or 4.8 for my LODX, and then for my LODY of about 15.9, both of those being ppm. All right, so that's step one. It's just kind of understanding this. I didn't require you to report this, but if you're wondering how it works, that would be how you would detect it. And so basically, based on the slope of this line, the more it's sloped, the lower your LOD. The more flat it is, the larger your LODs and your LOQs. And so basically with this one, anything that had an original or a diluted concentration greater than 16 ppm, it was supposed to do a good job of quantitating that sample. Okay, so then here, and so you will notice too that that is interesting, because our x-intercept, it was below 15.9. Okay, so we would need to go with a higher dilution in order to really use this for quantitation. And that's going to actually explain a whole lot of why there's error in this line. You might have gotten something very similar. Okay, so if you had done less dilution than what I did for this run, which was basically 20 microliter, 20, I probably did 20 microliters down to 25. If you had done something larger than that, you probably got better data. Okay, then within this, Now I told you that I wanted to do some linear analysis. So what I had done to try and make my data a little better was I noticed the viscosities. I said I wouldn't tell you, but I did. But the idea was water flows a whole lot faster than the corn syrup. So if you take your sample, which was in corn syrup, and try to compare it to your external calibration curve, that number is going to be way off. And in fact, it was. It was reading around 10,000 ppm. If I just plugged in these zeros here, if I plugged in these absorbances into my external calibration curve, I would have only gotten 10,000 ppm instead of 15,000, which would have been a huge, 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 huge error. So that 10,000 number would be about a 41% error, which is huge. With the standard addition analysis, we're getting around, whoops, I ruined that, a 15% error. And then if I use this flow rate compensation, that's around 7%. So how I accounted for it was I took graduated cylinders and I slowly sucked water out of them. I timed them 10 seconds apiece approximately, and then I looked at the rate, and the rate for water was a whole lot faster than the rate for just sucking up corn syrup. I found the average rates and the standard deviations, and then the percentage difference between the two was around 71% difference. So if I use that and I realize that the rate of corn syrup, so 1 over 71% is 1.41%. Okay, so if I look at, and that's not actually a percentage would be 141%. Okay, so if I looked at that number then and I multiplied my 9935 times that 441%, I get 14,000%, which is actually a 7% error. So there's lots of ways you can do this math. It's kind of fun, but I know some of you guys wanted to see it. And so here is the data for this. I don't want to just give you my spreadsheet because it has all this other stuff in it. Okay, but do feel free to play around with it and think about this and let me know if you have any questions. But as I said, kind of the main thing I wanted you to get out of this is that there's lots of ways, but you need to keep track of your error and you need to think about how to report it. So with this one, that was my final answer. You need to report a final answer that looks like this, that does error propagation, just like this, okay, using this big huge equation and using that data analysis tool pack in order to solve for your final answer.